Here we're going to look at something that is going to save us just an immense amount of time if we'll learn to do it properly, and that is the rational zero theorem. It's going to help me to find that first zero on those polynomial functions. So this is what the rational zero theorem says. If f of x is a polynomial function in standard form, meaning descending order on the powers of x, with the subscript of the coefficient equaling the power on x, and if p over q expressed in its lowest terms is a rational zero of f, then p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. What that is saying is that the only possible numerator for my zero is a factor of the constant term. And the only possible denominators for that zero are factors of my lead coefficient. That greatly limits the number of possible zeros that we need to check out. So let's take a look at what the rational zero theorem is telling us. If I need to find all possible rational zeros of f, then what I need to do is take a look at that constant term 3, find all factors of 3, take a look at the leading coefficient of 4, find all factors of 4. Then my only possible zeros here are factors of 3 over factors of 4. So that's 1 over 1, 1 over 2, 1 over 4. But it's also 3 over 1, 3 over 2, and 3 over 4. But the ones that we better not forget are negative 1, negative 1/2, and negative 1/4, and negative 3, negative 3/2, and negative 3/4. So we may not be too happy with all the fractions, but we've got 3, 6, 9, 12 possible zeros out of infinitely many numbers. So it really has cut it down in my favor if I've got to guess on which one's going to be my first zero. So let's take a look at an example of how the rational root theorem really helps me when I'm looking for zeros of a polynomial. Here's a polynomial, a third degree polynomial, and I'm looking for all zeros. Well, right off the bat, I don't think I'm going to be able to factor by grouping. So I'm going to come up here and say, well, I need all the factors of 2. That's my constant term. That's 1 and 2. All the factors of my lead coefficient. That's even easier. He's 1. So it's constant over lead. So it's 1 over 1 and 2 over 1. But I have to consider both positive and negative. But still, that only leaves me with 4 possible rational zeros. So that's not that many to have to use trial and error with. So I'm going to start with the 1, just because he's a good place to start. He doesn't always work for me. Matter of fact, frequently he doesn't. But 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. Plus negative 5 is negative 3. He is not going to work this time because that does not give me a 0. And that's okay. I haven't wasted a whole lot of time because I did it synthetically. So I'm going to get out my eraser and I'm going to erase all that. And then I'm going to try 2. Bring down my 1. 2 times 1 is 2, plus 1 is 3. 2 times 3 is 6, minus 5 is 1, and I just found my rational root. Because 2 times 1 is 2. When I add, I get 0. So 2 is one of my zeros. But now I have to deal with x squared plus 3x plus 1. And to find a 0, that means set it equal to 0. So I'm looking, and these are not going to be rational because factors of 1 that add together and give me 3 don't exist. So this is going to be irrational or complex. So I'm going to say, let's let A be 1, B equal 3, and C equal 1. And then I'm going to plug into the quadratic formula. X equals the opposite of B, plus or minus square root B squared minus 4AC all over 2A. So this is going to be negative 3 plus or minus square root of 9 minus 4 is 5 over 2. So there are my other two. So I have 3 real solutions, 2, the only rational one, and then negative 3 minus square root of 5 over 2, and negative 3 plus square root of 5 over 2. So sometimes it takes a little work, sometimes it takes a little luck if I want to get there quickly, because I use the rational zero theorem to give me the possibles for me to try in synthetic division. Sometimes it may be the last number I try that works, but as soon as I get that 0, I know that's a 0, and I break down a quadratic.